something called unsupervised learning, which is really easy, and text mining in a little bit of text mining with Weka. And then just finish up, make a little bit more clear what we talked about last week with regard to how the neural network learns. So we talked about it. It looks at the error that it made, and somehow it learns. We talked about that last time we mentioned something called gradient descent, but I just want to go into it a little bit more clearly. So those are the three things. And then in terms of homework and things like that, if you want to, and I don't recommend it, but it's certainly up to you. If you want to, you can do an individual project. So we had the group projects, and they were very good. So I decided that we don't need to have the individual project, but we do have a slot in our grading for individual projects. So that would just be subsumed in the group project. So you wouldn't need to do the individual, but since it's in the syllabus, I should give you the opportunity to do it if you want to. So if you want to do an individual project, and again, I don't recommend, at least not for most people, then you can. And that will be due in 10 days. So the individual project would mean you'd get a different set of data, and you'd basically do the same thing on the on that data that we did in the group projects. So I will make an assignment for that, and if you want to, you can do it. As I said, it's not required, but since it's in the syllabus, I really feel like I should offer it for anybody who really wants to do it. So I will make an assignment for that, and you can do it if you want. So I just wanted to let you know about that. Okay, so let's go to the first topic called unsupervised learning. By the way, are there any questions? Okay, unsupervised learning is an easy topic, but it's interesting to talk about. So let's do this. Let's see. Yeah. Okay. So unsupervised learning, and we're talking about something specifically called clustering. So let's talk about clustering. So classification versus clustering. So we've been talking a lot, basically we spent the whole semester talking about classification, or if you like, and we also did a little bit of prediction. So classification and prediction, the difference is if the output variable is numeric, we would call it prediction. And if it's not numeric, if it's categorical, then we call it classification. So we spent most of the time on classification. But usually regression is not classification, it's prediction, because the output variable is numeric. So at least in the classical regression. Now, some people use regression. Yeah, that's right. So anyway, yeah. So we did talk about regression. That's not classification, but anyway, but between what we've talked about, and we haven't talked about something called unsupervised learning, but classification is called supervised learning. And what it means is we learn a method for predicting the instance class. The instance means the example or the row of data. So we want to predict the row, the class of the row from pre-labeled classified instances. In other words, our data, how do all the algorithms we have, how do they learn? They learn because we have a training set. And what do I mean by we have a training set? I mean, we have, let's see, maybe we should make it clear by doing it like this. We have, our data look something like this, right? We have, whatever it is, column 1 might be, age and income and various, we have lots of variables, age, income, I don't know, country, nationality, else, school, blah, blah, blah. We have many things. And then we have the class variable that we're trying to predict. So maybe we're trying to predict favorite chocolate or favorite food, favorite food. We're trying to predict somebody's favorite food, and we have these other variables. So this is called the label. The thing we're trying to predict is called the label. So we have a lot of so-called labeled data. So we have, like, here's a person, they're 33 and their income is 55 and their nationality is A, whatever A is, and their school is whatever, GG, and their favorite food is tomato. Okay, tomato. And then we have somebody else and their age is 22 and their income is 33 and their nationality is X and whatever, right? And their favorite food is ice cream. Okay, so whatever, right? We have a bunch of data like this, and we call this labels, the labels. So we have what we call labeled data for our training set. Now, our testing set, we also have some, testing set data like down here, right? And that's our test set. And that's usually labeled also so that we can decide whether we made an error or not. So it's usually labeled, but it's not, like when you're doing this in a business, you don't have it labeled. You're trying to predict what should I sell to this person. And, maybe tomato is the best thing to sell, but you don't know that. So it's not labeled. So you're trying to make a prediction. Well, based on these variables, these inputs, I want to predict what I should sell them. And based on these, I want to predict what I should sell them. So this is called unlabeled data. There is no label here, whereas this is called labeled. So that's what we mean by labeled data. So going back to here, and supervised learning is when you have labeled data. So you would think, well, we always have labeled data. Well, that's right. So far, we've always had labeled data, but this is something we want to talk about, a kind of a learning that we can do with non-labeled data. So anyway, they say classification, supervised learning learns a method for predicting the instance class from pre-labeled, right? That's our training set, classified instances. Okay, so that's what we've done before. So like, we have here in this picture, we're only showing 2 input variables. So one of them is along the x-axis and the other is along the y-axis. And then we're plotting, and those input variables are presumably numeric. And then, so we're plotting them. So like, this is age and this is income. So this represents someone who has a low age and a low income. And this represents somebody who has a high age and a high income. Okay, so that's what we only see 2 input variables here. And it's kind of impossible in this kind of graph to show more than 3. We can show 3 because we can put a third dimension in here, but after that, you can't do that. But of course, our data, we have many, many dimensions, not just 3. But to make this kind of visualization, you can only show at most 3. And that's a little confusing when we have to look at a 3D graph. So, basically, it's only good for 2 dimensions in a way. Okay, but anyway, we have only 2 dimensions here, but we also have the class. The class is either, there's only 2 possibilities for the class. There's either there's either circles, which are blue, and squares, which are green. So the class variable here only has 2 possibilities, at least the way it looks here. Okay, so can we make a prediction based on this and this as to what class it's going to be in? Well, it's not so great, but maybe we could. Yeah, actually here, if we say the x variable, maybe I can label this. Can I label this? I don't think so. Oh yeah, I could label it with, can write with this, right? Let's see, pointer options, pen. Okay, so let's say the x-axis is the age, and the y-axis is the income. Okay, so if the age is between here and here, and if income is less than here, then we can predict, oh, it's going to be green, or it's going to be the square, whatever that is. And we can say if the age is above here, then basically we can predict that it's going to be the blue. So we can make some predictions based on this. Okay, so anyway, that's the kind of thing we've sort of talked about in the past, but we want to talk about something else now. Okay, so this is called unsupervised learning. And that's when we don't know any labels. We don't have any training set. We don't have any labels at all. We have unlabeled data. There is no, in fact, there's not even any class variable at all. All we have is a bunch of sort of variables, none of which is the class variable. Okay, so it's completely different than anything we've talked about before. And this is not used that often. In fact, it's not, I'd say it's used about 5% of data science focuses on this. But it's good to mention it, just so that you know, because we see that word unsupervised or supervised, and it's good to know what it means. So, what we want to do is find groupings in the data. So it finds natural grouping of instances given unlabeled data. So let's see what they're talking about. So here's a group. So what do we mean by it's a group? Well, we mean that there's a cluster here. There's a cluster here, and here's another group, and here's another group. Okay, so we talk about, first of all, we should begin by talking about what we mean by distance, because going back to this picture, why do these form one group? Because they're close to each other. So what do we mean by close? What do we mean when we say this is close to this? Well, in this graph, it's pretty obvious what we mean by close. But suppose I'm talking about a bunch of students. What do we mean by students are close? Or what do we mean by saying that students are similar? These two students are similar and these two aren't. What in the world does that mean, right? So here we have a pretty, we're probably, everybody's going to give the same definition of what we mean by these two dots are close. But if I say two students are close, I don't mean physically close, but I mean they're close, they're kind of similar. I don't think anybody's going to have, give the same definition. we're all going to have our own definitions. So we want to define what we mean by close. Now here, it's pretty clear. Most people will give the same definition of what we mean by close. But of course, close relies on the concept of distance. When I say things are close, I'm usually saying there's some kind of distance that I can measure. So, but that distance that we're talking about here, this way of measuring the distance, which I think most people know, like let's say, let me just go back here again and go back to here. And suppose I have another dot here and another dot over here in the same graph. And I want to know the distance from here to here. I think most people know that you can measure it using the Pythagorean theorem. So if I know the coordinates of this point, like this is 10, whoops, that never works. 10, I don't know why that happens. 10, whatever, 3, I can't write here. Anyway, if this is 10, 3, and this is 15, 2, then you know how to get the distance. I can't write here with this pen. I wish I could. Anyway, I'll try once more. 10, 3, and this is, say, 8, 2. Okay, so if we have those two coordinates, then I think most people know how to find the distance here to here. If we know this distance, and we do because, oops, I made a mistake. There is 8, and the distance here is 1, right? 3 minus 2, and 8. Okay, so this distance is, okay, this is 1 and this is 8, right? Am I right? Yeah. So then the distance here, we can use the Pythagorean theorem. But anyway, we know how to calculate distance in the plane. Okay, but if we have nominal attributes, then what do we mean by distance, right? If we don't have numeric data, how do we measure distance? And so those are some questions that we have with distance. And also we can say, are all attributes equally important? So maybe some of our variables in our data set are not very important, so we don't want to really include them much in terms of measuring the distance. Like suppose we're talking about the distance between two people, or how similar they are. We might talk about their income as one way to measure the similarity. So if they earn similar income, they're similar. We might talk about their age, and so if the distance between their age is not big, they're similar. And then, but what do we do with like pizza versus ice cream? One person likes pizza and one person likes ice cream. How do we measure that, the distance for nominal attributes? So these are the kinds of questions that we're thinking about. But anyway, let's keep going. Okay, so the idea here is that we want to find groups of individuals or groups of examples or instances. Remember, all these represent instances or represent individuals or represent examples. What did I say? Examples, instances, and so on. So how do we find groups that are similar? So, well, I can see here that this is kind of a group, and I can see that this is kind of a group, and I can see that this is kind of a group. Maybe I should even include that one. But I can see that, but how do we teach the computer to see that? So that's the question. We need an algorithm because our eyes somehow have some kind of ability to see this, but a computer doesn't have eyes. So we have to come up with some kind of algorithm for it to see it. So there are many algorithms that people have come up with, but this one is very simple, and yet it's still popular and it works well. So let's see how it works. It's called Kmeans. So the first step is pick. So what we're looking for is groups. So what we want to do is pick, find like the group center. So if I said this is a group here, I would say the center is about here. If I said this is a group here, I would say the center is about here. If I said this is a group, I'd say the center is about here. Okay, so we want to find those group centers, but we don't have it. The computer can't see anything yet. So all we do first is we pick centers randomly. So first of all, we have to decide, we have to tell the computer how many groups to look for. So that's sort of one weakness of this algorithm, is that the computer doesn't find the number of groups. We sort of say, we want to find 3 groups in this data, or we want to find 5 groups in this data, or whatever. So anyway, we'll say we want to find 3 groups. And so what we do is we pick centers for the groups just randomly, completely randomly. We just throw 3 dots, 3 centers here. Say, okay, here, put a center here, a center here, and a center here. Those are just random dots. And those will be our initial guesses for the center for this set of data, for 3 clusters or 3 groups. But we just set them randomly at first. So we set them up randomly like that. Okay, this is cluster 1, the center of cluster 1, center of cluster 2, and the center of cluster 3. Okay, now what do we do? Now we assign points to the different groups. So how do we assign points to this center, K1? We find the points that, we say, okay, what about this point here? What about this point here? Is it closer to here, or is it closer to here, or is it closer to here? Well, if it's closer to here, we'll assign it, we'll say it's in this cluster, but if it's closer to here, we'll say it's in this cluster. So we can do that because we know how far things are. We can talk about distance. So we can find out how far each dot is from each cluster and then assign it to the cluster to which it's closest. Okay, so we do that and we get that these are in one group, these are in another group, and these are in another group. Okay, next, what do? We move this to here. Why? Because if we have these red dots, this, we've already said these are the red ones, we can find the center of these red squares. And, you can find the center. It's not very hard. So the center apparently is here. So we're going to move this from here to here. Same thing here. We're going to move this one from here to here, and this one from here to here. We can find the center of these green ones, and it's here. We can find the center of these blue ones, and it's here. So we move these to the new places like that. Okay, now we have this picture. Now, though, we just moved our clusters, or I'm sorry, the centers for our clusters. We just moved them. So there's a chance that, maybe this dot used to be closer to here, but now it's closer to here. Or there's a chance vice versa, that this dot used to be closer to here, but now it's closer to here. And there's a chance that like this dot used to be close to the red, but now it's closer to the blue. So what do we have to do? We have to check again to see which center this should be associated with, and this one, which center every dot should be associated with. So we reassign points closest to a different new cluster center. So we do, so we say, so which points get reassigned? Well, maybe this looks too far away now. So maybe this should be a red one. And this one, maybe this should be a blue one. I'm not sure, probably not. And how about anything else? I don't know. Let's see what they say here. So these points are going, well, sorry. This point gets moved. This point, I guess, will get moved. And this point, I guess, will get moved. So these 3 points will now shift. So this one will become what? Green? Maybe. This one will probably become red. And maybe this one will become green. Let's see. Okay, anyway, so now, yeah, this one became, oh, it was red. I don't know. Anyway, never mind. So now what? Now, since we just reassigned some of the points to new groups, now the centers are going to change again. So maybe now the new center will be here. And now this new center will be here. And now this new center will be here. So the centers will change. So they move. Now what do we do? Now again, we have to check. Is this point really associated with this center, or is it associated with this center? Is this point really associated with this center, or is it associated with some? So we keep doing this over and over again. We keep doing it until nothing changes. When nothing changes, we stop. And now we have identified 3 clusters. So that's the idea of K-means. So we choose 3 means, 3 centers. That's what the K stands for, the number of centers we're going to look for, or the number of groups that we're going to look for. And then we can find groups. Remember, we just had dots in the plane. We just had data. And now we've put the data in groups. So, maybe these groups mean something. Like maybe, we take our data and they are our customers, and we cluster them into similar groups, and maybe they're similar. Maybe their buying patterns will be similar. Maybe, and this isn't just used in business. This is like used in genetics and working with diseases and finding genes associated with certain diseases and things like that. It's used in many places, actually, but not nearly as much as the other, or at least as far as I know, not nearly as much as supervised learning. This is called unsupervised learning. And but anyway, we might say, okay, maybe these are like young people who like sports, and these are middle-aged people that like shooting guns or something, and something else, right? So we might find similarities and sort of try and figure out, who are these people? Why are they similar? Who are these people? Why are they similar? Who are these people? Why are they similar? And so we can sort of segment our customer base with this. But as I said, this is not just used in business. Okay, so that's called unsupervised learning. So let's go on now. Okay, so let's go to Weka and talk about text mining a little bit. So actually, before class, I went to this site. I went to TripAdvisor. Actually, I went to TripAdvisor and I looked for hotels in Fukuoka. And if you go here and you go to hotels, and actually, wait, I want to go to, oh, here. So I found this hotel, which is a fancy, supposedly fancy hotel in Fukuoka. It's pretty expensive. And actually, the reviews are not too good for this hotel. But anyway, that's That's the way it goes. Anyway, you can get reviews here. So there's this many reviews. So if I click on them, I can see them. And I used to work with this data a long time ago, maybe 10 years ago. This site was very new, and I scraped this data, and I had about 400,000 reviews in a database. Now they don't let you do that. Now they tell you can't do that anymore. But back then, they were they didn't stop you from doing it. But anyway, we have reviews. So here's a review. And I guess there's actually more to it. And then here's a review. And actually, these reviews are not very good, actually. But anyway, so what I did is I just copied a few reviews. Of course, I don't want to do a lot. So I did this, and here they are. So this one said good, and this one said something, and this one said something, and this one said something, and this one said something else. So these are the reviews. And then I read the review, and I decided, is it positive or negative? So I said, this is positive, this is positive, this is positive, this is zero, this is neutral, and this is negative. Now, so I had to label I had to give these labels myself, based on the text. Now I remember just now, I just remembered that how I did this before was I used this to measure this. So is this positive or not? So I don't have to read this and decide myself. I used this to measure whether this was positive. So this would say it's not very positive, and this would say this is not very positive. So I didn't have to read all those 400,000 reviews that I had and decide for myself, are they positive or negative? I used this instead. So that certainly makes things easier. But I mean, and that's probably a pretty good measure of whether this is positive or negative, right? This is, obviously the person who wrote this did this. So they know whether this was positive or not, and this should reflect that. So this is actually a very good measure, maybe even better than I could do if I read it, or at least I'd say it's just as good. But anyway, here I didn't do that. I just decided myself by reading it whether these are positive or negative. Okay, so we have this file, and we want to do text mining. What that means is I want to build some model which can take text like a review and decide whether it's positive or negative without knowing whether it's positive or negative. So I want to take this or this or this and say, obviously I don't want to take those because I already worked with those. Those are part of my training data, but I'll have some, new review, and I don't want to read it. And maybe I don't have this. I can't look at this. I only have the text, and I want my model, my engine, to be able to make a prediction about whether this is positive, negative, or whatever. So I have to train a model to do this. And I'll use this data, all of this data, to train it. So I'll take this text and say that's positive. And I'll take this text and I'll say that's a positive. And this one, and so on. And then I'll put that into, I have to figure out some way to put this into Weka though. And because J48 doesn't know what to do with this text, and neural network doesn't know what to do with this text, and whatever, all the other ones that we talked about. Random forest doesn't know what to do with the text. So I have to figure out some way to give this data to random forest or neural network or J48. So how do I do that? Well, somebody started working on this in the 70s, 1970s, and came up with a very good idea. So what we do is we take all of our training data. Now, of course, we don't usually have just 6 elements in our training data. You know, hopefully we have like 10,000 at least elements in our training data. Anyway, we take all of this, whatever, hopefully we have 10,000 rows, and each one consists of a review. And so there's going to be a bunch of words altogether. If I take all of them, you know, how many different words, unique words are there in, you know, my 10,000 reviews? Well, you know, probably, I don't know how, you know, probably there's, let's say, about 5,000 different words altogether, different words. So, you know, obviously they're going to have the word train station, and a lot of them are going to have hakata, and a lot of them are going to have, you know, bed and food and room and pool, right? So maybe there are 5,000 different words all together in all of the reviews. So what I do is I write them all down. So I say, well, there was the word outstanding, and there was the word room, and there was the word hakata, and there was the word bed, and so on. And I just write them all down here. Now Weka is going to do that for us, but we write them all down. And then what we do and so this list here is called the dictionary. So the dictionary is here. That's called the dictionary. Okay, now I have review 1. Here it is. I'm going to put it here. Now it shouldn't go all the way there. But anyway, so review 1, I see it has the word outstanding, so I'll put a 1 there. And does it have the word room? Probably it does, but I don't know. Well, let's say it doesn't have the word room. So it doesn't have the word room, but does it have the word hakata? I don't know. Maybe not. But it probably has the word bed, and so on. So I do this. I take the first review and I do this. Now you could say, oh, well, it has the word bed 2 times. And, you know, so you could do it that way, or you could just say, does it have it or not? So those are 2 different schemes that we could play with. So you might have just yes or no here, or you might have this actually represent the number of times bed occurs in this review. So you do this, you have this entire 5,000 word dictionary, and each one of these has a pattern here, and a different pattern for each review. So this review will be different. So what we're doing is like, let's say, and so on. What we're doing is we're representing now, we have a numeric representation for each review. So this review is 1, 0, 0, 1, blah, 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 blah. And this review is 0, 1, and so on. So we have a numeric representation for each review. And then don't forget that we also have this. Well, we also have that. So we can treat these as variables. You know, usually in our data projects, we have our class variable, and then we have other variables like, you know, age and income and so on. And then we use these to predict this, right? Somebody's age is 33 and their income is 55 or 22. And here this person is 22 and their income is 75 and so on. So we use that to predict the class. So we're doing exactly the same thing now, but the variables happen to be different. They're, you know, this and this and this and this and so on. So those are our variables, and they seem like kind of weird, like kind of a weird variable. Bed is a variable, but that's the variable, whatever it is. And we have actually 5,000 variables now. Okay, so we have 5,000 variables by which to make a prediction about whether something is positive or negative. And so we can do it. We can put this data into any of our algorithms. We can put it into the neural network. We can put it into random forest. We can blah, blah, blah. And so we've converted our reviews to this big set of variables, or we could call it like a matrix. But anyway, we've put it into this big set of variables, and we can use them now to predict. And then if we get a new review, you know, in our test set, or like we just have a new review, like I think that the hotel was too hot or something like that. So now we just transform this into this, and then we can put it into our algorithm or our model, and it will say, oh, I think this, it will say, this is positive, or this is negative, or this is neutral. And so we have, and we can, of course, we can do testing as well, because if we have 10,000 rows like this of labeled data, we can split it into 6,000 for training and 4,000 for testing. So we can test how well it does, and then we can try it on a new. So that's the idea. We can try it on a new review. Okay, so how can you do this in Weka? You do this. You go to Open File, and you find that one that I just had. I think it's in Downloads. And I want, it's a CSV file. So it's Hyatt here. So I open it up, and you can see I have it. And if I click on this, you can see the reviews here. So in the class, I'm sorry, and here, this is, I don't know what this is, positive, negative. Why? What are these colors? I guess it's treating this as the class. Yeah. Anyway, we don't want it to treat that as the class. But anyway, so now we have it. Now we have it in there, and this is numeric, and that's, well, okay, that's numeric, and this is nominal. Okay, now we have to do a little work with Weka to transform it into what we said. We want to transform it into those vectors, that matrix. So we have to do a few things. The main thing that we use is something in here, and we're working on the attribute, I think, yeah. And anyway, it's this thing, string to word vector. So this kind of representation that I gave over here are called word vectors. So that's what we want to get. So I want to get this thing. I want to use this thing. I want to convert it to a word vector, and that is done with this thing here, string to word vector. But this is not a string, this is nominal. So string is another data type in Weka. So we have to convert it first from nominal to string. So let's do that. There should be something that allows us to do that. So we find, is there something that goes from nominal to string? So nominal to string here. So we want nominal to string, and we only want to convert the last attribute here, the review attribute. So we do that. and we just do it. And now it is string. Of course, we can't see what it is anymore, but that's okay. It's now string. Okay, now we go and we use that other one. We want to convert it to a so-called word vector. So now we use this one. Now let's see some of the options. Now there are many options, and we don't have time to talk about this, but this is a whole, actually just this thing here is sort of a whole class in text mining. Now this is not the most modern approach to doing this, but it's got a lot of stuff in it that you could learn a lot from. But we don't have time to do all of it. But one thing I'm going to do is I'm going to make all of the words into lowercase. So remember we talked about these words here. I want them all to be lowercase. Now, I'm not going to go into why we do that, but as I said, it's kind of a long topic, so we won't go into it. But I'm just going to do that just for fun. It's not really necessary at all, but I'm just going to do it. And one other thing is like this is, we usually use this thing called a stemmer, but I won't talk about that, at least not yet, not now. But wait, we want to go to one more thing here. Where did it keep talking? I guess that's all. I thought there was another thing. Now my screen doesn't allow me to see this. I can't set it. Oh, there it is. Okay. There was one more thing I wanted. Oh, here. Here, you see what it says? It says dictionary. So we can see what the dictionary looks like. So let's do that. Let's call it Hyatt Dictionary. So we can check it out, see what it looks like. Maybe I'll call it Hyatt Dictionary.txt. I don't know if that works. Yeah. Okay. Anyway, I'll do that. Okay, and then I have to push this up so that I can. Oh, there it is. Okay. So now I can click OK. And now oh wait, one more thing here. First to last. No, I don't want to do it to this variable. I only want to do it to the last variable. So I don't think it's going to actually make any difference, but okay, and then apply it. Okay, now what did we say was going to happen? We said we were going to take all of our data, and we were going to make new variables, all these variables. And what did we do? Let's see. How many variables are there? A lot. Remember, this is the list of variables. That's what we usually see here. So these are all variables, all these words. And there's 228, including the positive negative one at the beginning. So that's what we have now accomplished. We took all of that data and we made it into a dictionary, and they're the variables. Now, if you want to see that dictionary, where is it? Let's see if I can find that. Here it is. No. Well, here it is. Okay, let me open it. No. I'll open it with this, maybe. Okay, so this is the dictionary that it created. And I guess this one this probably tells us how many times it occurred in the entire data set. But anyway, we don't care about that. But all we care about is, this is maybe king size bed, and this is location, and the mall, because that hotel is located in that Canal City Mall in Fukuoka, and so on. So we have that. So we did that. And it's also here. Okay, so now we're in the ballpark. Now we can start to, basically we're set. We can, there's one more thing. One more thing I want to do. I'd like to look at this file. Like we just converted the data to a new file. So let's save it and look at that also. Or maybe we don't need to do that. We can just edit it. We can just look at this. So you can see that we had, how many rows of data did we have? We have 1, 2, 3, 4, 5. Those are the instances. And you can see that here. This is the first instance, it was positive. And then this is the word vector. And here's the second one. And this is the word vector. And this is called, by the way, a document. Well, let me write it down. This is called a document term matrix. So why is it called, and there's an alternative, it would be a term document matrix. So what's the difference? So it just tells you this is the row, and this and term is the column, and or we could reverse it and have the term be the row and the document is the, but we have what? The document or the review are the different rows. So each row is a different document, and each column is a different word. So it's called a document word matrix. Okay, that's not too important, but I mean, if you're going to study this, you would want to know that. Anyway, so now we have it. This is our data. This is what we can work with. Now, of course, we only have 5 instances. We're not going to get any good results from this in terms of, we need like 10,000 or at least 200, more than that. Because we have so many variables, you need more data to make a good model. So we have 280 variables, 228 variables or something like that. So we really need at least, let's say, 1,000 rows of data to make a good model. But anyway, we're just going to see how you do it here. So let's do that. Now, the one thing we have to do, though, is we have to tell Weka that this is the class. So one way to do that is just to right-click on this and just here, turn this one into the class variable. So you can do that easily like that, and then click OK. And now it pushes positive, negative all the way down to here. Before it was up at the top, but now it's down here. Okay, so now Weka knows that this is the class variable, and we can do anything now. We can do any of the algorithms. We could use 0R. We can do, oh no, sorry, we can't. What's wrong? Oh, one more problem, and that is this is numeric. So that makes sense, right? The review is numeric, right? 1, 0, and -1. So it makes sense that it should be numeric, but in terms of the algorithms we can work with when it's numeric, we got a lot of grayed out stuff here. That means we can't work with those. And like J48 doesn't work because J48 doesn't want to have a numeric output variable. So we have to, so we don't have to, but it might be a good idea to convert this to nominal. Now, you lose something by doing that, because once you convert it to nominal, Weka doesn't know that 0 is in between -1 and 1. because it's not a number anymore. It's just a name. So you lose that. But you get to do all these other models. Well, I'm sorry, all these other algorithms. So it's up to you. You might not care. So actually, random forest will work either way, I think. So let's just try random forest before we go any further. And let's use the whole training set because percentage split is kind of silly. We only have 5 elements in our data set. I don't know, it doesn't really, none of this will make any sense. It's not very useful. We need many more rows of data. But anyway, let's just do it, see what we get with random forest. Okay, so it got a correlation coefficient. So notice that when we don't have a nominal output variable, we don't get a confusion matrix, because confusion matrices are for nominal output variables. So we're not going to get that. So we do get this, the correlation coefficient, which is kind of a measure of how well it did, and it did very well. Okay, anyway, let's go back and convert this to nominal. So I think everybody knows how to do that, but you go from numeric to nominal, there. But we want to be careful. We don't want to convert all of these from numeric to nominal. So we only want to convert the last variable from numeric to nominal. So we'll just apply it to the last one, and then we can apply it. And now we can use J48, for example. Okay, J48. So let's try it. Okay, so it got 80% right, but this is meaningless because, first of all, we tested it on the training set. So that's very bad practice to do that. And also it's only 5 pieces of data, so it's just silly. But we're just seeing how to do it. I don't want to collect, 100. I don't want to copy and paste 100 reviews. So anyway, this is just the idea of how you can treat text, and you can build your own sentiment engine from this. So you can rate things, this is positive, this is, you could make your own sentiment engine. You don't need to rely, like at the very first lecture of our class, we used RapidMiner to measure the sentiment of tweets. But you don't have to rely on somebody else's engine. You can build your own. Of course, you have to collect a lot of data to do it. But this is how they do it. They collect a lot of data. They set these up so that they know their training data is positive or negative, and they can build this engine. Now, there are neural network approaches to doing this, which are different than what we're doing. It's somewhat different. But anyway, this is a classic way to do this. And here we can see the one error that it made. And what was that? This is the true value was neutral, and it classified it as 1, which is, besides A, which is negative. Okay, so anyway, so that's the idea behind text mining. Now, there's many other options that we could go to in terms of this thing, and you would want to learn about that. But we only have limited time. We can't study everything. So, but there are many options here. For example, this one, if you look at these things, you have 2 separate variables, one called staff and one called staffs. Now that's not really, I don't think we really need to have, we would want to have, I don't want to say that, one person mentions staffs and the other person mentions staff, and those would be considered different. I would want to measure those 2 people as different, because this one person had a 1 here and a 0 here, and the other person had a 1 here and a 0 here. So we would say they're different, but I don't think we want to do that. So, and the same thing with many cases here, like stay and stayed, and you know, many here, high and higher, maybe high and higher might be different, but like here, allowed and allowing, no. Those should probably be collapsed into one vector. I'm sorry, one attribute. So, but it didn't do that. So, but we could get it to do that. Now we have to go backwards, undo what we did. So undo, undo, undo. Okay, then we can go back here. Now again, we only want to do it to the last thing. But what we could do is we could use what's called a stemmer, and that cuts that kind of reduces the word. So we have the word allow and allowing, but it just kind of cuts it down to some kind of basic root word. So let's just check that out and see what happens. There's this thing called stemmer in here, and you can choose from different stemmers, and as I recall, a good one to use is the snowball stemmer. So let's use that. And what else did we say we wanted here? Forget, what else did we do here? What else did we do? Did we do anything else? Oh, we did, sorry. We did this one. And we did last. Okay, let's try it. Let's see what happens. Now let's see what our words are. So now we still have allowed and allowing. Huh, I didn't think that would happen. Let me just do that again. Oh, we also need this. Oh, I did that. Well, I wonder why that didn't work. Usually that would work. Stemmer. Oh, let's see here. Well, I don't know. Usually it would collapse these two words into the same one. So I'm not quite sure why it didn't work. Anyway, that's enough for text mining. Basic introduction to text mining. Okay, now let's go back to one last topic, which is this one. Well, anyway, one last topic. Okay. So, anybody have any questions before we go on? Okay, let me switch to and here and here and share the screen and this one. Okay, so we talked last week about how a neural network is going to learn, and I want to just make it a little bit more clear here. So, you know, we talked about the fact that we would have a graph. We could talk about a graph where E is the error in our prediction, and we have a weight as the x-axis. And we said that, the error is going to depend on the weight. So maybe the error is high, and then it drops down, and then it goes back up again, depending on the weight. So if I have a weight here, W1, then the error is up here. But I would like to find the weight here. We'll call it W star. I'd like to find that because that represents the lowest error for my network, for my training. So we said that's what we're trying to do. Remember, we have a network. Let's say we just have a very simple network. So it's just this. So we only have one weight, and we have only one input. And then we, of course, we multiply this input and this weight, and we get x1w. And then we usually say we have some threshold function in there, like the sigmoid function or sigmoid function, the S curve. And then we output the result, and that is, we label that as y hat. That's our prediction. And we talked about if this was Apple stock, and if it was Apple stock, maybe we make a prediction of $950, but their actual price today was $900. So we made an error of $50. That was our error. So, so we'd like to adjust our network now so that maybe we won't make that error next time. So the question is, how do we adjust it? Sorry. So the question is, what do we do? How can we fix the network so that it's better? Well, we can't change this. This is, that's the price of, that's the input to our, whatever data we have on Apple stock. That's what's going in there. We can't change that. We can't control, the information about Apple. So we can't change that. The only thing here that we can change is W. So that's what we have to change. So we have this error, and so we have to change W somehow so that maybe it would have predicted closer to 900 instead of 950. So we have to change W somehow. So that's what we mean in this graph. We want to move W somehow, change it so that it gets reduces the error. In this picture, it looks like I should, if this was my W, it looks like I should move W in this direction. Now this picture has nothing to do with the Apple example. It's just I just made up this picture. But if this picture was the way things were, and I was out here at W1 out here, then I obviously want to decrease W1 to reduce the error. And if I was over here at W2, then I don't want to decrease W2. That's going to increase the error. I want to increase W2. That's going to decrease the error. So, if this picture represented the way things were, then that's what we would need to do. Now, as I said, this picture has nothing to do with Apple. It's just in general what we, just illustrating what we would need to do in different cases. So, but we can use as our signal about what to do. In other words, what to do means, do we increase W or do we decrease it? So we're going to have a way to decide that. And the way we're going to decide that is like this. Consider this line. And consider this line. Okay, now what are these lines? We talked about this at least somewhere at one point. These lines are called tangent lines. And we can get their slopes. You know, each one has a slope. This line has a slope, and this line has a slope. So they each have slopes, and we can find those slopes by using calculus. We can find those slopes by calculating the derivative. So the derivative will give us the slope. Now, what good is the slope going to do for us? Well, what are we trying to do? We're trying to decide, should we increase W or should we decrease W? That's what we're trying to decide. And what good will the slope do in doing that? Well, let's see if it can give us any good clue about what to do. Well, let's see. Let me change this color. I'm going to call this one green and then call this one yellow, just so I can use those words. I'm going to call this one yellow. Okay, so for the green one, is the slope positive or negative? So let's say green, is the slope, green M, is it greater than 0 or less than 0? Anybody want to answer that? The slope of the green line. Anybody still here, or did you all go to sleep?
It's greater than 0.
Okay, great. The slope of this is greater than 0. That's right. Right? This is an increasing slope here. Increasing slope. Okay, now how about for the yellow line?
I don't see a yellow line.
Yeah, okay, sorry. Why is this doing that? What's going on here? Something's wrong with my system. I wonder what's going on here. Oh well. I know something's wrong with this. This is the yellow line.
It's still greater than 0.
Slope is what?
Still greater than 0?
No.
I mean lesser than 0 then.
Yeah, the slope, the yellow M is less than 0, and the green one is greater than 0. Okay, let's see. Let me call on somebody here, see if anybody else is awake or even here. So how about this person? Are you here?
Yes, Professor.
Okay, great. So the green line, is the slope positive or negative?
The green line. You mean the one with the green arrow?
Yeah, the one with the green arrows.
Is positive.
Okay, and how about the yellow arrow?
The yellow one, the slope is negative.
Okay, great. Okay, now, so we need to know whether to decrease W or increase it. Now, when we're over here at this W here, do we want to increase W or decrease it? Anybody?
Decrease.
For this W here,
I think decrease.
do we want to increase it or decrease it?
I think we should decrease it.
We want to decrease it, right? Because we want to move to here. So we want to decrease it. Now the slope at this point is what? Is positive, right? So, you know, it sounds like if the slope is positive, that means we want to decrease W. Now, how about over here? When we are over here, do we want to increase this W or decrease this W?
We want to increase the
We
W.
want to increase it. The slope is negative here. So it sounds like if the slope is negative, that means increase W. So if the slope is negative, which is what it is here, then we're going to make a rule, and this makes sense if you think about it. It's not just, you know, it doesn't just happen right here. The same thing here and here. When the slope will be negative here, slope will be negative here, slope will be negative here. So all of these, when the slope is negative, this rule makes sense. If the slope is negative, increase W. And on the other hand, this rule also makes sense. Here, I don't really have any space. Well, anyway, if slope is positive, then decrease W. Okay, we have the rule for what to do. If we can find the slope of the E curve, this is our error curve. If we can find the slope of our error curve here, then we know what to do with W. If we can find the slope of the E curve, then we know what to do with W. That's the way it's going to be done. That's the way the neural network trains itself. It checks the slope of the error at the particular W that we have. And if the slope of the error is positive, then I made a mistake here. The green M, oh, no, I didn't make a mistake. Sorry, that's right. Sorry about that. That's right. So if the slope is positive for the E curve, we know what to do with the weight. If the slope is negative for the E curve, we know what to do. That's how the neural network trains itself. Now let's look at this in action. But let's just write this again, just so we don't forget, and maybe a little easier to read. So if slope, I'll just say M, is greater than 0, then decrease W. If M is less than, well, actually I want to do that in the other color. That was yellow. If M, can I change this or not? No, what is going on there? It must be the connection. Oh well. If M is less than 0, then increase W. Okay, so we made note of that. All right, now let's try and do a little even more specific. So let's take our network, and we're just going to take the simplest possible network here to do the math as the first example of the math. So we're going to have an input X, just one input, and we're going to just have one weight. And then we're going to have Y hat as the prediction. Okay, now normally we would have in here a function, but the math becomes a slightly bit more complicated, and there's no reason to make the math more complicated the first time through. So let's just leave that out, at least for the first time. So we won't say there's a threshold function. Okay, there's no threshold function. So we're only dealing with this super, super simple situation. And then we could, make it a little more complicated by putting the threshold in there and doing the same kind of calculation again. We'd have a little bit more complicated calculation to do, but it would be basically the same thing. So anyway, let's do it without that to make the math as simple as possible for the first time through. So, of course, what we get here inside is X times W, right? That's what we do, X times W. But we're not going to put that into a sigma function, which would mean put that inside sigma, but we're not going to do that. We're going to make it easier, so we're not going to do that. So in other words, Y hat is just going to be XW. So this is the simplest possible scenario we could come up with, and it will, but we can improve it, make it better by including more features, but right now we're just doing that. Okay, so anyway, what is the error? So the error is what? Anybody want to tell me what the error is? An expression for the error? Anybody want to tell me what the error, an expression for the error is? Okay, well, remember we said that we might get, our prediction might be 950, but the real price is 900. So in this case, what's the error? Can anybody tell me that? That's easy. How about Alexa?
It's 50.
Yeah, it's 50. So that's easy, right? But I want to write it more generally. So I'm going to remember which one of these is Y hat? This one or this one? Which one is called Y hat? About how about Kabir John? Can you tell me? Which one is called Y hat? No, Kabir John? Okay, but how about Arai-san? Can you tell me which one is called Y hat? Arai?
Yes.
Which one is Y hat of these two?
Oh, Lit one.
Which one?
Lit one.
Y. That's right. Why is that true? Did you just toss a coin to get that answer?
No.
That's not a good way to do it.
Yeah.
Okay, well, remember I just said we're predicting 950, but the actual price is only 900. So what do we call the prediction? Y hat. Y hat stands for the prediction. So Y hat is 950. And what do we call the actual price? We call that Y. Okay, so we need that notation. We have Y hat stands for the prediction, and Y stands for the actual price. So what's the error? The error is 950 minus 900. What is that? That's 950 is the Y hat, and 900 is the Y. So that's the expression for the error. Y hat minus Y, or you could do it the other way around. Y minus Y hat. Okay, so this is the error. The problem is though, well, I don't know if it's a problem, but this is going to be, could be positive or it could be negative, right? Y hat minus Y could be positive or it could be negative, but we don't want that. We don't want it to be positive or negative. We want it to always be positive. So of course we could do something like this, Y hat minus Y absolute value. That's always going to be positive. But instead of doing that, we can also do this square. So that is how we're going to define the error here. So it's not just going to be Y minus Y hat. It's going to be Y hat minus Y squared. So that it doesn't, I'm not sure, maybe we could have done it with just Y minus Y, I'm sorry, just Y hat minus Y and not had the square there. But anyway, we're going to use the square. Okay. Now again, we're talking about this simple network. It doesn't even have a threshold function in it. So it's just a simple network, no threshold. Okay, so now, so we can write the error in terms of, what we need to do is write the error, I'm going to call it E. What we need to do is write the error in terms of W. I want to write this. Why is that? Why do I want to write it like that? Because the whole analysis that I said up here was based on finding the slope in the EW plane. So EW plane means I'm thinking of E as a function of W. So, you know, whenever I write the EW plane, the idea is implicitly I'm saying that E is a function of W. So I want to write E as a function of W. So I want to write E as a function of W. But I don't have E as a function of W here. I have E, well, I have E right here. It's not a function of W. It's just Y hat minus Y squared. So can anybody see how I can write E as a function of W? Right now, I only have here. This is E. So not very good for me. I want to do that other analysis about derivatives. And to do that, I have to write E as a function of W, but I don't see E as a function of W here. I have E equals Y hat minus Y squared. So I don't have E as a function of W. So I'm angry. I'm upset. I'm frustrated. I'm confused. I can't do what I want to do. So can anybody see how I can do this? E as a function of W. I'm confused, angry, upset, frustrated. I can't do anything. I don't have E as a function of W. I want E as a function of W. I want it like I want a piece of chocolate. I really want it. How can I do it? Yes?
Can you change y hat into w times x?
Yeah, exactly. What is Y hat?
Y
Y
hat
hat is so simple in this, I made this as simple as the simplest possible neighborhood. We don't even have the, we only have one input node. We only have one weight, and we don't even have a threshold function. So it's pretty simple. But anyway, what is Y hat in this super simple scenario? Well, I think I wrote it somewhere, or maybe yeah, here. Actually, I should have put Y. Yeah, I have Y hat there. So that is Y hat up there. So Y hat is just X W. Okay, and that's what she said. She said, I can write Y hat as a function of W, and then E is going to be a function of W because E has Y hat in it. So now I'm going to get E as a function of W because I can write this as XW minus Y squared. I have it now. E is a function of W. So why did I want that? Because I realized that if I can get the slope of it, then I can do this rule. If the slope is positive, decrease W. If the slope is negative, increase W. So I'm on my way now. I'm ready. I can almost have be able to use my rule, but I need to get the slope now. The slope of this EW curve. E is a function of W curve in the EW plane. Well, I have this. And all I want to do is get dE dW. In other words, I want the derivative. So I want the derivative of, now I know for a very few of you, or at least some of you, that the derivative is, maybe you didn't study that. But I know we went over it before, and maybe that wasn't enough. So I apologize in that case. But for some of you, the derivative, you understand it. And we did talk about this briefly. I don't consider it that we talked about it sufficiently for this to be very good, very clear, but I'm going to present it. So anyway, we want this X W, here it is, minus Y squared. We want the derivative of that. Okay, that's pretty good. Because, for example, suppose I said this. What's the derivative of W squared dW? If those of you that know calculus, you would be able to do this. Can anybody tell me what it is?
2W.
2W, right. And if I ask you what this is, what's the answer?
5W.
5W to the fourth, right?
Yep.
Right. So yeah, we know how to do derivatives, supposedly. And this has a W in it. And we're talking about dW. So this shouldn't be all that hard. Now I did try to introduce or remind you of a rule when finding derivatives, and that is the chain rule. And that will allow us to do this particular problem. Because here we have an outside function and we have an inside function. So that's the chain rule. That's what we need to find this derivative. And we can write it as I'm going to call this purple thing. I'm going to call the purple thing something. I forget. What do I call it? What do they call this? What's the general word for this? Okay. Well, I think I should have probably called this. Well, I don't want to go into that. Okay, I'm just going to give this a name. I'm going to call it difference. Diff. I'm going to call it not diff because I already used D here. I don't want to use diff. I'm going to call it subtract. S-U-B. Okay, it's this minus this. So I'll call it subtract. So the chain rule can be written like this. If I call this sub, S-U-B, then the chain rule can be written as dE d sub times d sub. You know, I just using that word. Just it just stands for this purple thing. Maybe I should only use one letter, not S-U-B. Maybe I should call it D-S. I'll call this whole thing not D sub, and I'll just call it D-S. This is just S, so I'll just say S there. Okay, so that's S. So it's dE ds and ds dw. So dE dw by the chain rule looks like this. So we want dE ds. So this thing is S. So the answer turns out to be 2S, and then ds dw is just it's just one. No, it's just X. Sorry, X. So we get that, which we can now replace S by this thing. So we get 2xw minus y times x. This doesn't look right for some reason. What did I do wrong? I think it's right. It doesn't look right. 2 xw minus y. Looks right though. Okay, it doesn't look right, but it looks right. Okay, did anybody see I made a mistake here? I think it's 2xw minus y
It's 2W.
times x, right? Is that right? Uh-oh, we're running out of time. Okay, anyway, so this is the answer. And now, what was the whole deal? Why did we want to do this? Because we said, if the slope is positive, then we're going to decrease W in order to improve the performance. And if M is negative, then increase W. Now we have some expression for the slope. That's what the derivative tells us. It tells us the slope. This tells us the slope. And now we have an expression for it here. And the expression has X's in it. It has W in it. It has Y in it. And it has a 2 in it, and it has a negative sign in it. Well, some of these, I mean, all of these are already known. X is the input, so that's known. W is the current value of W, so that's known. Y is the true price, so that's known, and 2 is known. So everything in here is known, so we can calculate DEDW. And that is the basic idea of backpropagation. So if DEDW is less than 0 when we do this calculation, then the rule, what we came up with is we should increase W. And if it's greater than 0, then we should decrease W. And that's it. That's called, this whole thing has a name. It's called backpropagation. It's the way the error is calculated, and we sort of going backwards. Backpropagation. Now, when we go from this direction and we get the output, that's called forward propagation. Forward propagation is when you put in X, you put in a 3, and the W is 2, and you multiply 3 times 2, and you get 6 here, and blah, blah, blah. That's called forward propagation. And back propagation is when we do this derivative, figure out the sign of the derivative, and that will tell us whether to decrease W, and this will tell us how to learn, whether to increase or decrease W. Okay, that's it. That's all we have time for. So thank you all for joining the class. I hope you now think that you understand this field called machine learning, data science, and AI, because you do. You have a very strong feeling for it now. Of course, there's a lot more you can study. And if you wanted to become a data scientist, you'd have to study a lot more. But basically, you know what's going on. So I think that's great. And so anybody talks to you about data science, you already did your project. You know what it's about. You know that it's about making predictions. You know that there are algorithms.